In Chapter 10, we are talking about power for computers, and the material in this lecture is a supplement to, not a restatement, of material in the chapter in your text. You will want to read the chapter to get all of the information. When we talk about power in PCs, there are several different areas we have to consider. First, there are the concepts of electricity itself, wattage, amps, voltage, and ohms. Electricity is simply groups of electrons flowing along something that allows the electrons to move easily through it, known as a conductor. A good example is copper wire. Electricity is similar to water, both because it flows and because we can use similar terms to describe this flow. We can measure the pressure that pushes electrons across a conductor, and that pressure is voltage, measured in volts. Current is the amount of electrons flowing. This is measured in amps, the amount going through a circuit every second. When you multiply the measurement of pressure, or volts, by the measurement of amount, or amps, you get watts, which is the measurement of power, or how much electrical work can be done with that power. Very few conductors allow electricity to flow freely and easily. Most have at least some resistance to the flow of electricity. We can also measure this resistance in units called ohms. Things that hinder the flow completely are called non-conductors. Electrons tend to flow from where there are many of them to where there are fewer of them. Areas where there are more have a negative polarity, and the areas with fewer have a positive polarity. Current is what can kill people when they get an electrical shock, either from a high voltage power line or the capacitors inside a monitor or power supply or similar device. Alternating current flows alternately in both directions, but direct current flows steadily in only one direction. All electrons basically have one desire, and that's to get to ground, literally. We've captured these electrons and made them flow through conducting circuits to serve our purposes. But if there's a break in a circuit, those electrons will seize the chance to take a shortcut to ground. We call this, of course, a short circuit. The text goes into more detail on all of these, as well as other items, but these basics will get us started. We must also understand what a PC's power supply does and how it works. The transformation of AC, or alternating current, into DC, or direct current, and the higher 110 voltage down to 12 or fewer volts is also covered in the book. Of course, the presence of capacitors inside power supplies must always be remembered. This is what makes opening up a power supply dangerous, and it should never be attempted without proper training and safety precautions. In other words, if you are going to do it, have someone who knows how show you first, and don't be grounded. At some point, you may need to test the power output of your outlet and/or your power supply. There are several devices that will handle this. A circuit tester can tell you if your AC is in the proper range. A power supply tester will tell you if a power supply is providing enough power of the right amounts to your system components. A multimeter, otherwise known as a volt-ohm meter or digital multimeter, will do both of these tasks. Again, the book gives details on how these devices can be used. Another thing to remember is that whatever power is not used by the computer is given off as a byproduct, and that byproduct is heat. If there is no power, there is no heat. When there is power, there will be heat. And in a closed system such as a computer case, you have to pay attention to that heat. How much is there? What is generating it? How can you minimize the amount given off? How can you get it away from the components that are generating it and are most sensitive to it? These issues have become more important as devices in PCs have become faster. The faster something runs, the more heat it produces. This is true of things besides computer components as well. In the earlier days of computers, when processors ran in the 25, 50, or 75 megahertz range, we didn't worry much about heat. The motherboard bus speed was 33 or 66 megahertz, and just about everything else ran at a third or half of that speed. A single power supply fan took care of any heat issues inside of a case. Speeds are now much faster. In the case of processors, they are thousands of times faster. Bus speeds, RAM speeds, video RAM, and graphical processing unit speeds are all much faster than 10 years ago. Heat sinks, multiple fans, liquid coolant systems are all being used to dissipate the heat that is generated inside of computer cases. Temperature sensors can monitor heat levels of individual components and of the case interior, turning on additional fans as necessary or shutting down components. Today's computer systems are actually designed to provide airflow over components that need it the most. Remember that one of the most basic properties of hot air is it rises. This is true inside your PC case as well. By taking this into account, you can more effectively cool your computer system. Cases today are often constructed with vents in the bottom front of the case. Cool air comes in here, often aided by intake fans. This cooler air flows through the case, rising as it warms by drawing heat off of components. Even though it's warmer as it reaches things like your video card, RAM, and processor, the movement of the air helps cool these devices, aided by their heat sinks, heat spreaders, and fans. The power supply serves another purpose here besides just supplying the proper power and voltages. Vents in the bottom and sides of the unit, as well as power supply fans, draw warm air into the power supply, and the exhaust fan on the back sends it out of the case. Often this process is aided by a case exhaust fan mounted right underneath the power supply. When computer components started picking up additional speed, the layout inside of cases and on motherboards was redesigned to improve cooling. Today's motherboard and case layouts actually do assist in the flow of cool air in from the lower front and the exhaust of warm air out of the upper back of the case. So how do you know if you have overheating problems? One of the main signs is random lockups and/or shutdowns. These can be caused by overheating of individual components such as video cards, processors, or even chipset chips, which makes identifying the problem more challenging. Another challenge is that overheating problems may only become apparent after a system has been active for a certain amount of time. A system that stays on all day but goes into power-saving modes when not in use will probably not have heat-related problems in those circumstances. But use that same system for an 8-hour gaming session and it could be subject to overheating. What was adequate cooling protection for general use may not be a good match for the intense system activity that gaming demands. This is why, when you're troubleshooting lockups, reboots, and shutdowns, it's very important to ask not only what was being done at the time, but what was the system activity for the prior hours. In one of this chapter's labs, you're going to take a look at different ways to figure out how many watts you will need for any given PC's power supply. If you want to get really technical and involved, you can add up the power requirements of every drive, every expansion card, every USB or FireWire device, along with the motherboard, lights, and everything else that is powered from your system's power supply. This can be tedious, and it can sometimes be hard to determine just how much power something actually draws. Remember that something undergoing average use, such as a video card processing text, is drawing less power than when it's processing 3D action graphics. This is a good explanation of why gaming PCs often have beefier power supplies than a system meant for casual home or business use. It's important to know that not all power supplies are created equal. Two power supplies may supply the same wattage, but one may be cheaply made and fail sooner than the other. A general rule of thumb is, if two power supplies are equal in wattage, the heavier one is better because it probably uses a bigger transformer, bigger heat sinks, and more quality components. It will probably also be more expensive, but if you are trusting all of your other sensitive, expensive components to it, you don't want to go with the cheapy bargain model. Also, not every power supply will fit into every case. Just as there is variety in sizes of cases, there is variety in the physical size of power supplies. The form factor of the power supply must also match the form factor of the motherboard and therefore indirectly of the case. In other words, an AT power supply won't plug into an ATX motherboard and probably won't fit into a case that would hold an ATX board. One exception is the so-called BTX form factor. There really is no such thing as a BTX power supply. You just need to find an ATX power supply that fits into a BTX case for a BTX board. These are important considerations when you're upgrading a system or building a new one from scratch. Often, people buy a case that comes with a power supply, and they buy the case for looks. Given what we've just talked about, the looks may not be conducive to a good design for dissipating heat, and most of the time, the power supplies provided are undersupplied. It's a bit more challenging to buy a separate power supply that will fit into and work with a well-designed case, but it's by no means impossible. You just have to pay attention to things such as what components you're going to put into the system and how it's going to be used. There's something to be said for making the power supply choice one of the last decisions in an assembly process. You also need to be aware of the amperage ratings on the various voltage lines of the power supply. The 12-volt line is the one that powers all of the drives. If the total amps needed by all of your drives exceeds the amps provided by that 12-volt line on the power supply, you will have a non-functioning drive if you attempt to use all of them at the same time. Again, this is not necessarily something you'd need to worry about under average use, but if you multitask, you might run into problems. Power supplies now also come with a variety of connectors for different devices. ATX power supplies may come with these: the 24-pin main ATX power connector to the motherboard, or a 20-pin connector with a separate 4-pin connection. This would be main power to the motherboard with motherboard connection for the processor. The 15-pin SATA drive power connector, an 8-pin 12-volt connector for the CPU, 6-pin power for PCI Express video cards, the 4-pin Molex, which is the large white power connector for PATA hard drives and optical drives, the 4-pin Berg mini connector, or the small white power connector that's for floppy drives, and a 3-pin connector used to monitor fan speed. Sometimes power supplies don't have enough of the ones you need for connections. Splitters can help here, but a new development is the modular power supply. With one of these, you can connect just the power cables that you actually need. This will eliminate that tangle of extra wires that hangs inside the case and impedes the airflow. Another area we need to be concerned about when talking about power is protecting our systems from either too much or too little power. Both situations can cause damage to our components. Most over and under voltage issues are related to the power coming into our homes or offices. Standard voltage is somewhere between 110 and 120 volts, and this amount is what our power supply and other devices expect to receive. Undervoltages can occur during periods of peak electrical usage, such as very hot days during the summer when many air conditioners and fans are running. Some areas of the country experience rolling brownouts, periods of time when less voltage is available due to increased power use. In extreme cases, this can become rolling blackouts. There's another danger associated with power outage, not when the outage occurs, but when the power is restored. When the power comes back on, it often comes on with a surge. If your computer or other electronic equipment is plugged in and was already on, that surge is going right into your components. If the surge is minor, the power supply may be able to compensate with minimal effect. If the surge is larger, the components can be damaged or destroyed to the extreme where your power supply is also fried. To prevent this situation, when the power goes off, turn off and unplug your computer equipment, especially if your system is connected directly to the outlet. Even if using some kind of power protection device like a surge suppressor or UPS, turn off and unplug that device. The biggest power surge of all, of course, is lightning. So another good time to turn off and unplug your case and monitor or laptop or their power protection device is when a storm is coming. At the first sound of thunder, I recommend saving your work, shutting down, and unplugging. And don't forget to unplug your connection to the internet. Phone or cable lines are as vulnerable to lightning strikes as power lines are. Unplug the phone or cable that goes into your power protection device or that comes out of the wall jack. Now you are using some kind of power protection, right? If, after a storm, you reconnect the power and turn your system back on and nothing happens, don't panic. If things were off and unplugged, they should have suffered no damage. Check the outlet with a lamp or a radio and make sure that a circuit breaker or fuse wasn't tripped or blown. Now it's true that every once in a while coincidences do happen and some damage becomes apparent when a system is off during a storm. The two things may not necessarily be cause and effect. Troubleshooting and power. Some symptoms that may be caused by the power supply include a squealing or other loud noise as soon as the system is powered on, nothing happening when the PC is turned on, system freezes before the operating system loads, random shutdowns, blue screen errors. Now, these things can also be caused by other problems, which makes power problems some of the hardest to pin down, troubleshoot, and fix. About the only consistency in power problems is their intermittent, inconsistent nature. If you suspect that the power supply is underperforming or failing, or if the power supply fan no longer works, the best thing to do is simply replace the power supply. Testing output with a multimeter can let you know what amounts the power supply is providing to the motherboard and drives, but it can't tell you how much power your system is drawing at peak load. It also can't tell you if the power from the outlet is inadequate or problematic. There are outlet testers, but again, these will only tell you what the output is like at any given moment in time. I've run into situations where the output is fine in the morning, but later in the day, when more things on a circuit are drawing power, the output is inadequate. The age of wiring in a structure can sometimes be a factor, as can where you are located on a power line run be. If you are toward the end of the line and someone further up line draws large amounts of power at different times, you may be undersupplied at those times. Electric welding equipment, for example, is a heavy power draw and can affect the neighbor's power. A line conditioner or a UPS with line conditioning feature may help in this situation. It's going to be cheaper than moving. The important things to remember about power are, do you have enough? Do you have enough of the right voltage, and is this voltage steady? Is your system protected from too much or too little power? Remember to take these things into consideration when troubleshooting problems, as well as when building or upgrading a system.